Are you going to be? I need your help with something. Trying to figure out these last two.
So this one. Let's see. So that one will be
And A squared. So basically, A squared would be
Monday. Did you get 5 on, or 4 on 3.5? I keep getting the same thing, like I don't understand how I'm wrong. Gracie got the same thing.
Did she ever get it right?
Nope. Then I Googled it, and I got the same thing when I Googled it, and it's wrong. Like I don't understand.
No, because I can't figure out the last two.
because
There's a couple of them I probably with the last two.
I hate it.
And I'm working on number 11 right now.
I know her.
Really, yeah.
That's the only one I don't.
Yeah. Did you get 135?
What did you get?
135.
I don't know.
Because it's a prism.
What is the example for?
That's what I was going to ask her in class, like when, because everyone says see example. So I thought, look in my book.
Here.
So I looked in my book. Thought maybe it was related to the book, but
It's
it's
not.
not.
Which one did I get wrong? I have this one wrong because I used 1/2 instead of 1/3.
I did
This one too.
I did the radius I saw for R and got the radius, and I'm like, oh, oops.
This one I only did length times, or you did x times s and then.
That's what I did.
Subtracted them, and I was like, how is
Well,
that
I did
wrong?
S times S times S, and then I did X times X times X, and subtracted that, and I was like,
She's trying to flip it.
I'm like, oh, the height of that would be S. But
Yeah, but surface area, I'm taking a turn for the worst.
yeah, because this is a,
Just the triangle ones confuse me, but triangle and those.
well that, yeah, so it's a prism.
Number 11.
So
I need to start printing out minutes instead of writing just drawing them down.
it's better, I think, personally, but
Even pressure.
volume of a prism, area of the base times the height.
Okay,
Okay,
that's not
so the area of a triangle is 1/2.
because you got the negative 1, 2, 3, 1 half. Thank you.
A times B, so it's the legs, not hypotenuse. So it would be A times C times height.
Because if you divide -1 by -2,
Because it's a 90-degree
positive
triangle.
To be
So the legs are A and C.
right?
Yeah, so I even did like the Pythagorean theorem and made sure that that was A and B, and it was. It's A and B. So I did 1/2 times A times
See, that's what I don't understand. What
is 270, and then half of that is 135, because the height is 0.5. So I understand why it's wrong. But which one? Oh, Janet, Grace didn't get that one either. Oh, you know why? Because we never learned that formula. It's like,
The nose cone one too? The nose cone question?
oh, the nose cone.
I don't remember learning that at all.
No.
Because I asked Gracie, I was like, I looked in the book and I looked in the past and I was like, here are the cones. And I did, and then it was wrong. And then with the-
Oh, yeah, I had a, because it's lateral area,
So you don't have to do R twice?
the question is lateral surface area. So it's lateral surface area is pi r times square root of h squared plus r squared. When we
See, this one, A, for number 11 is all,
How long did Mr. Burke?
meaning every, right? And then B is exists, there exists.
I don't remember.
Yeah, here's what this proves.
One on the
Did you?
which is mix them up, like I'm
I
doing.
know that the rational order, rational
what did you,
This one I haven't even turned on because I don't
That's, I
understand.
just don't understand. Which one?
okay.
Every single one can prove every single one.
Right. 24, that one.
Well, I'll show you how I did mine.
Yeah, that one, I just said.
You have to do the multiplication.
The equation I got was
I,
So I'm definitely gonna ask that.
on the say, like, the practices it. Very end, the last question is the same, like, the last two questions would be.
it's a stream
Find it,
equation.
since a rational number is a rational number. That's a r squared, and 3r squared, 2r, all rational.
Right, right.
See, the -2 would be what we have in
I don't think.
because I'm going with all numbers.
I don't know anymore.
Is it just me or is it like?
Oh, mine was.
Ice cold.
Y is the height. B1 plus B2.
The exam.
Yeah.
Yeah, I don't know how deep we're supposed to go with it.
Right.
And that's times 2 because there's 2 of them.
I just went through and said, what is it? And this is
Well, it's that whole thing
the
times 2.
four. Some of it, there's.
I just rewrote it. Yeah, I just said X.
And honestly,
And I did it is B2 times
Actually, I
height.
couldn't remember what
B2 times height. And then this
I
one is
remember I put that
Here's
as half inch.
plus. And this back one
it's going to be
is
A implies B. What it implies B. 2 is A. I wrote like, so I replaced A for X just to so that's
All right, let's get started. Check attendance first.
kids B squared.
Megan. Here.
X.
Elsa. Lisa. Here.
So if I did
Morgan.
Here.
b squared divided by
Allison.
a squared.
Here. Katie.
Here.
Jesse.
That's all.
Here.
Leah. Here. Catherine. Here. Madison.
Loved it. I just want to keep it how it is.
Madison. Curtis.
Here.
Okay, so first there is homework assignment due today. Do you have any questions about the home assignments?
Yes.
Okay, which one?
3.2, number 24.
One, two, number 24. Okay, so let's take a look at example. I did see, I think, Morgan, you already turned in your homework assignments, right? I didn't go through that. I think if you want to fix that number 24 and email to me because you already submitted, you probably cannot, you cannot submit again, so you can email me number 24, just the number 24 again, you can. So, I can give you an example here, kind of similar to this. So before we look at the question, so the problem asks us to prove. So it's given. What's given? So let's write out if R is any rational number, then so we want to prove. Let's see if I can use. I will just change some numbers. Minus 3R plus 2 is rational. Okay. So before we do this, recall the definition of a rational number. What is the definition of a rational number?
Integer over integer.
Yes. What did you say, James? Yeah. Well, yes, can be written as a fraction, but to be more precise, what is a fraction? What does a fraction look like? It's what the other student said, integer over integer. Yes. Okay. So to be more specific, the definition of a rational number is has to be integer over integer. So kind of like a fraction. Okay. So this is what you need to show. When you look at this, 5R squared minus 3R plus 2, it doesn't look like an integer over integer at all, right? So you have to have this format. Integer on the top over divided by integer on the bottom. So when you look at it, it's not in that form. So you have to change it to that form. Well, what we start with, because the hypothesis, this is a conditional statement. So this is like given. So under this condition, if we know R is a rational number, you can prove 5R squared minus 3R plus 2 is rational. We're going to start with a rational number R. So let R be equal to A over B, where A and B are both integers. Why can I do that? How can I assume R is an integer divided by integer? Because it's given, right? Because the problem says R is a rational number. By the definition of rational number, R should be able to have this form, integer divided by integer form. Okay, so now we're going to plug it in here. So 5R squared is 5 times R, replace it with the A over B. Minus 3 times R, which is A over B, plus 2. But don't stop right there. I think that's, Morgan, I think that's what you did. So far it's correct, but you have to continue from there. Because when you look at this, excuse me. Does this fit our definition, integer over integer? Does it have this form, integer divided by integer? Not yet, right? If you look at this, it's, it has a lot of things. It's not really, the format has to be this. a single integer on the top, an integer on the bottom. You cannot have something plus something minus something plus something. So it does not have that form yet. But we got to use algebra to continue to change this, to work this out, simplify it to get a single integer on the top and a single integer on the bottom. Okay, so by the order of operations, you got to do the exponent first, which is, what's a over b squared? How do we do a over b squared? A squared over b squared, right? So you can either do it by definition or do it by a over b squared means multiply 2 copies of a over b. You get an a squared over b squared. Or you can use one of the formulas, exponential rules you learned in algebra class or calculus class. We also use this, and to get a squared b over b squared. Okay, exponent first. Make sure you do that. Follow the order of operations. Exponent go first. And then you're going to do multiplication. I guess we can do all of these multiplication in the second step. So in the next step, we work out 5 times a squared over b squared. What is that? You can put a 5 over 1. Yes, 5a squared over b squared. Minus 3 over 1 times a over b. 3a over b, right? Okay. And plus 2 you can put it in the form of fraction, 2 over 1. Now, we got to do subtraction and addition. How do we add or subtract fractions? Find the least common denominator. In this case, what's the least common denominator? B squared, right? Can everybody see what the least common denominator is? That's again from the algebra class. So the least common denominator is b squared. So the first one is already b squared, so keep it. Second one, we need to multiply both top and the bottom by what? In order to get b squared? By what? B, right? Okay. The third one, what do we multiply? B squared. So we can get the common denominator, a matching denominator b squared. So now we have the common denominator b squared, and top we have 5a squared minus 3ab plus 2b squared. And look at this final simplified answer. So after all that work, we found out 5r squared minus 3r plus 2 can be simplified as 5a squared minus 3ab plus 2b squared over b squared. Does this fit our definition now? Or as a rational number? Yes? Again, the rational number is the integer divided by integer. And look at the top. Is this the integer? Yes, because remember when we started, a and b are both integers. If a, b are integers, when you do all the operations, square or multiplication, addition, subtraction, you should also still get an integer on the top, and the b squared, of course, is integer. So look at the top. Although it's a long expression, it doesn't look like a number, right? But you should know, as long as we know what a is and b is. Say, if a is 3, b is 4, you get 3/4, and you should be able to get a single number on the top, a single integer on the bottom. So that's exactly the integer over integer. So we can say since 5a squared minus 3ab plus 2b squared is an integer, and b squared is also an integer. We know this is a fraction, rational. So 5a squared minus 3ab plus 2b squared over b squared is rational. Okay, so we're done. So this pretty much proved that something we are very familiar with. We know that if r is a fraction, when you square it, you still get a fraction, times by 5, you still get a fraction, minus fraction, plus a fraction, you still get a fraction. We know that is true, but this is the formal proof for that. Previously, maybe in algebra class, it's like a common sense. Everyone knows that's true, but we proved it by the definition. Okay, so we started with a over b because a is a fraction, or a rational number. And we did all those operations, square, multiplication, addition, subtraction. We can still get a rational number because it's integer divided by integer. Okay, is this clear? Yes, thank you. Okay, good.
Would
Any
we
other?
do the same thing for 14 on the practice exam?
Okay. 14.
That would just be like the same type of thing, correct?
That's what I did.
Oh, number 14 on the practice exam. The only difference is there's over 3 there, right? Divide by 3 there. You do have to be careful because I did know that some students in the past made mistakes in the algebra part. So how do you do? I'm going to do like so r squared over just over 2, just for example. Oh, r squared over 2. So we assume r is a over b. The other part should be similar, minus 4r plus 2. You should be able to do the same way. But how do you work this out? A over b squared divided by 2. You can still do the top, which is a squared over b squared. But how do you do over 2? Does everybody know how to do that? Huh? Say it again. By 2 over 2? Or
just
this can be considered as, what does this line mean here, right? This line. Division, right? Okay, so if this confuses you, you could change it to the traditional symbol for division. It's like doing a squared over b squared divided by 2. How do we do divisions of fractions? Multiplying by the reciprocal, right? The inverse, right? Keep, change, flip, right? So you keep the first fraction, you change the division to multiplication, and you got to flip this number 2. How do you flip 2? Yes, you have 1 under there. You flip 2 over 1, you get a 1 over 2. So if this form confuses you, you can change it to division and do multiplication, multiply by the reciprocal, which gives you that. Okay? All right? So in your practice, then you had divide by 3. You should also do that. You cannot, I guess, when you work this out, you do have to change it to that single form. And then you can continue to add or subtract the others. Okay. All right, make sense?
Yes.
Any other question? No? No more questions? Okay. All right. So like I said, the homework assignment is due today, and also the practice exam. So let's see. So if you need to submit to Blackboard, practice exam 1 is under week 3. I can go ahead and move it to week 4, so you can submit everything under week 4. Okay. So anyway, so if you want to submit it to Blackboard, you can go to week 4 and click on both to submit both assignments there. Okay, I think so. Next Monday, it will be our first exam. So on Wednesday's class, I will. By the way, so you make sure you turn in the practice exam on time, because I need time tomorrow to grade all your practice exams, so I can give them back to you. I will give feedback to you on Blackboard on Wednesday, because on Wednesday's class, I'm going to go over the problems on the practice exam to answer your questions and to give you solutions. So you won't be able to turn in late. You won't be able to turn in this after Wednesday's class. Oh, I forgot to check. Is John there? No? Okay. Now, so next Monday, you still come to whatever your classroom is, and I will, this week, I guess, probably after Wednesday's class, I will send the test to your contact person for RULM classes. So you just come to the classroom, just take the test, like any other traditional classes. All right, today the exam will cover up to last Wednesday's class. So today's topic will not be on the exam, will not be on the first exam, it will be on the second exam. So today we're going to look at a new, by the way, so on section 3.3, divisibility, I only had time to give you like maybe 2-3 examples. Do you need more examples? So did you have trouble doing any of the homework problems? Let's see. Take a look. Like 26, did you have trouble doing 26? No? Okay. If not, okay, we can move on to 3.4. So 3.3, if you remember, we did some sections 3.1, 3.2, 3.3. We talked about something called direct proof and a counterexample. So pretty much if a statement is true, you prove it directly. If it's false, you give one counterexample. So 3.1, we talked about like even or odd integers. 3.2, we talked about rational numbers. And 3.3, we talked about divisibility. So what it means when you have like n divides, d divides n. What does it mean by definition? So today we're going to talk about 3.4 we're going to do by cases. Do the proof by cases. So 3.4 we learn a new technique, proof by cases. It's still considered as direct proof, but you won't be able to prove it by one case. You're going to have to do it by 2 different or 3 different cases. So a lot of times, like when you have a very complicated problem. So for us, most likely you can do it by 2 cases. The problems you're going to get, because this is your first proof class, you're going to do proofs by 2 cases or 3 cases. Like a lot of papers I published, I may have like 5 cases, and under each case I have sub-cases. So, because usually for very complicated theorems, you have to do many, many different cases. So this is a very common proof technique that we use in mathematics. So, like I use this, proof by cases all the time in the papers that I published. Okay, so let's look at. Before we look at the problems, we want to go back to look at integers. So we know integers. We have, like 0, positive 1, or negative 1, positive 2, negative 2, positive 3, negative 3, and so on. So previously we did prove a question. If an integer is even, then the square is also even. Okay, we proved it directly. If you still remember how to do that, so that example, if you have an even integer, so we start with the even integer. And then we square it. By algebra, we got 4k squared. And 4k squared, 4 can be factored as 2 times 2. And so we got 2 times the integer format, right? So that's, you can see easily why this is an even number squared. So we start with the even number because it's 2 times integer. And after we square it, we still get a 2 times integer, so which is still even. So that's the example we did before. Very easy, one step, no cases. But sometimes later, some of the problems, like in this home assignment, you won't be able to prove it by one case. For example, try to see if you have anything like. We can look at this homework assignment right here. Number 26. prove for all integers n squared minus n plus 3 is odd. And what kind of numbers is odd?
2k plus 1.
Yes. 2k plus 1 or 2k minus 1. So the format here for odd integer is, if you want to prove any number is odd, you have to have 2 times, that k just represents an integer. So I'm going to use the word here, integer. 2 times integer plus 1, or 2 times the integer minus 1. Now look at the homework question. They want us to show n squared minus n plus 3. So if you try to do it like the way we did before, okay, so we want to try to get this format, plus 1, right? So I can get 1 out of this 3, which is 3, I can rewrite it as 2 plus 1. That's fine, so I can get that plus 1 there to match the form I need. So the rest of them will be like this form. N squared plus n, minus n plus 2 plus 1. Here's the problem. In order to show this expression is odd, you will need to have factor out 2 from there. Can we factor 2 out of n squared minus n plus 2? Can we? No. Well, there is a factor 2 here, but there's not a factor 2 from n squared minus n. So there's no way you can just prove this is an even number. So pretty much it left for us to show this is even, and plus 1 will be odd, right? So here's the question: how do we show n squared minus n plus 2 is even for any integer? For any integer n, for any integer n. So that's the question. Because from what we learned before, the examples we did before, okay, you need to factor out the 2 here. You got to write it as 2 times the integer, which means you need to factor out the 2, but we can't. There's no way to factor out the 2. There's not a 2. So what should we do? We get stuck right there, right? So we have to use a new way, which is proof by cases. If you try to plug in some numbers, say if n is 1, 1 squared minus 1 plus 2 is 2. It is even, right? If n is 2, 2 squared minus 2 plus 2 is 4, still even. If you try 3, 3 squared minus 3, 6 plus 2 is 8, is even. And try 4. Looks like any integer I plugged in, yes, I do get an even number. But you cannot use that as a proof. It's just some examples. It tells us to prove this for any integer. There are infinite many integers. We cannot plug every single integer there to show this is even. So what are we going to do? Okay, so go back to, so why do we talk about proof by cases? For questions like this, you cannot factor out the 2. You can do it by cases. So how do we do by cases? Go back to look at the integers. All the integers we have, we can divide them into different categories of different types of integers. So, for example, I'm going to just draw a big circle to represent all the integers we have. Now, I want you to divide all the integers into 2 categories, not missing any integer, and any integer can only be in one of the categories. How can we do it? There are different ways. Any ideas?
Positive and negative?
Yes, that's one way, positive and negative. Well, if you do positive and negative, you're missing one. There's a 0, right? 0 is neither positive nor negative. Or you can consider both positive or negative. Usually we consider 0 as neither positive or negative. Any other way?
Odd or even?
Yes. Okay, this is the one we're going to take. Okay, we're going to take odd or even. Any number, think about it, any integer. It's either part of odd number or part of the even numbers. It won't be both, right? You cannot have a number that's both odd and even. So it will not be in both categories. And do we miss any number? Do we have a number that is not even, not odd? Do we have any number that's neither even nor odd?
0.
0 is considered as even number. Can you tell why? Check the definition. What's the definition of even number? 2 times an integer, right? So all these definitions that we talked about before on last Wednesday, have to memorize. It's really by, I think you know that before, it's just we need you to write as 2k, right? But in your mind, when you memorize the definition, you can memorize it as 2 times the integer. So can we write a 0 as 2 times the integer? Yes, right? 2 times what integer is 0?
0.
Yes, so 0 is considered as even, okay? It fits the definition of even integer. Okay, so that any integer you have, it's either even or odd, right? You're not going to miss any number. And it won't be any integer cannot be both even and odd. Okay, so how do we divide it? How do we describe an even integer symbolically or by algebraic expression? 2 times integer, we usually write it as well. 2k, and k is the integer right there. And odd integer, we write it as 2k plus 1, which is the odd integer. So we have 2 cases. So if you try to prove something that is true, so I can go ahead and look at an example now. If I want to prove, maybe we can do 2 and plus. Okay, so here I'm going to do example right here. Prove for any integer n. Prove that for any integer n, 2. I'm just going to do n squared plus m plus 8 is even. This will be our example 1. Now, the first idea is when you get a problem, get like this, we can try to use what we did before. If you can just do it by one case without doing different cases. So I have n squared plus n plus 8. I want to show it's even. And even, the definition of even is 2 times the integer. So you need to be able to write this as 2 times some kind of integer. But is it possible to write n squared plus n plus 8 as 2 times something? In other words, is it possible to factor out a 2 from this expression? No, right? There's not a 2 there from n squared or from n. Although there's a 2 as a factor of 8, we don't have there, so you cannot factor out a 2. So we're going to do it by cases. Case 1. N is equal to 2k. Sorry, case 1, where k is an integer. And leave a little bit of space right here because we also have to do case 2. N equals 2k plus 1. K is an integer. Now take a second and look at these. Why are we doing this? So first of all, the reason I have to do cases is because I cannot factor out a 2 from the original expression. And why do I do these 2 cases? Well, why would these 2 cases work? They ask us to prove for any integer this expression is always even. But any integer can be, any integer you have, it's either even or odd, right? So my approach is, since I cannot prove it directly, I'm going to first prove this is true for all the even integers. So if this n is even, I can show n squared plus n plus 8 is even. But that's not enough, right? Because they tell us to prove this is true for any integer. If you only prove for even integer, you didn't prove it for what if n is odd. So that's why I have to do the second case. If n is odd, I can still show this is an even integer. You see what I'm doing here? Is that clear?
Yes.
Yes? Okay, good. Well, so let's see, under case 1, so we're going to prove it by 2 cases. Case 1, assume this n is an even integer. That's why you can rewrite it as 2k now. Now plug 2k into the expression n squared plus n plus 8 equals, I'm going to replace that n with the 2k. 2k squared plus 2k and plus 8. Simplify 2k squared, we get 4k squared plus 2k plus 8. Now look at this new expression we got. Can we factor out the 2?
Yes.
Yes, which is 2k squared plus k plus 4. And we know that's an integer, right? Okay, so that part is the integer there. So we can mark this as even. I'm kind of out of space, so if you want to add a sentence there, say, since 2k squared plus k plus 4 is integer, 2 times this is going to be a even number. Okay, so therefore this is even. Okay. All right, so far we proved if this n is an even number, n squared plus n plus 8 is even. Don't forget the problem tells us to prove for any integer. So we're going to try to see, what if n is odd? If n is odd, can we still show n squared plus n plus 8 is still even? So we're going to plug 2k plus 1 in there. So replace n with 2k plus 1 squared plus 2k plus 1 plus 8. So we use algebra. You either use the formula, well, by the way, yes. How do we work out 2k plus 1 squared? Okay, yes. So you can use the FOIL rule or just distribution. But be careful. Is 2k plus 1 squared equal to 2k squared plus 1 squared? No, be careful. Don't do that, okay? This is a common mistake in algebra class. And when you do this, you have to do 2 copies of 2k plus 1. So you got to do FOIL, okay? Or if you have memorized the formula, you can do that. So you should get 2k times 2k, which is 4k squared. And 2k plus 1, that's 2k. 2k times 1, sorry. 1 times 2k, that's 2k, and 1 times 1, which is 1. Combine these two like terms, you are going to get 4k squared plus 4k plus 1. Okay, so please don't try to do 2k squared plus 1 squared. You're going to be missing a term right there. So I'm going to go ahead and copy this down there to my problem right here. 4k squared plus 4k plus 1. Okay. You can work it out just under there. You don't have to do on the separate paper. So this is 4k squared plus 4k plus 1, n plus 2k plus 1 plus 8. Now we're going to combine like terms. There is 4k and the 2k, and there are some numbers we can combine to get 4k squared plus 6k plus 10. Now, can we factor out the 2? Yes, so we get 2k squared plus 3k plus 5. Now, again, this is an integer since 2k squared plus 3k plus 5 is an integer. 2 times integer, of course, it's an even number. We can say n squared plus n plus 8 equals 2 times this integer is even. Okay. Any questions? Now, so go back to look at this proof one more time. So what did we do? We did 2 cases. And what's the reason we have to do 2 cases? Because when you look at the original expression, n squared plus n plus 8, if you only know n, there's no way you can factor out a 2 there. We get stuck right here. But we notice that if I do cases, so first I prove this is even for all the even numbers, n. And then I prove this is still even for all the odd integers, n. And then we proved it for every integer, right? Because all the integers can either even or odd. So either way, we can factor out the 2. See, if it's even, I can factor out the 2. If it's odd, I can still factor out the 2. Okay, but you may not always have two cases. Like I said, a lot of papers I published on discrete mathematics, I may do like 5 cases, or under first case, I may have a subcase 1.1, subcase 1.2. So really, if you have a complicated question, you may need to do many cases. How many cases do I need to? The next example I'm going to give you will be 3 cases. Sometimes you may have 4 cases, 5 cases. I try not to give you too many cases because this is, again, it's your first class, proof class. But you need to get an idea. It depends. How many cases you have depends on the question. And the other thing is, after the next example, I will explain how would I know I should do 2 cases, not 3 cases, for this problem. Or how would I know for the next question I have to do 3 cases, not 2 cases? Or how would I know some problem I don't even have to do cases? Like I can get it. We can get it just directly by 1 case. Okay, so again, the next question, I think a homework question, you may only have 2 cases. Later on the practice exam, second, when you prepare for the second exam, you will have 3 cases. So let's see. Go back to look at the integer again, all the integers. Now have 0, 1, 2. So previously, we divided all the integers into 2 categories. Any integer we have, it's either here or there. If it's not odd, then it has to be even. If it's not even, it has to be odd. But any way that we can divide it into 3 categories. 3. Yes, that's one way. So positive, negative, and 0. But for our problems, a lot of times, how would you describe a positive integer? There's no easy way, right? So for even and odd, you can describe it as 2k, 2k plus 1. So positive, negative, and 0. That is an option, but unfortunately, for the problems we're going to do, it will not work. For some other questions, it may work. So, any other way besides even and odd? Does anybody have any idea? If not, we go back to look at this one more time. So we're going to take a different view at these. Instead of calling them even numbers, there's a different way to call even numbers. What do we call them? 2 times something.
Divisible by 2?
Divisible by 2, yes. Or a multiple of 2, right? Okay, so I'm going to take this way. A multiple of 2. What is an even number? It's a multiple of 2. By looking at the definition, 2 times the integer, that's a multiple of 2. Okay. Well, so what about an odd integer? It's a multiple of 2. It's not a multiple of 2. And it will be multiple of 2 plus 1, right? So this will be a multiple of 2 plus 1. And another approach, take any integer. So if I ask you, any integer, when I ask you to divide it by 2, what are the possible remainders will you get? Or, yes. So any integer divided by 2 has 2 possible remainders. It's either 0 or 1. Remainders. 0 or 1. Could the remainder be 2? No, if the remainder is 2, you can continue to divide by 2, right? Okay. So any integer you have, let's say 17, if you divide by 2, you're going to get a remainder of 1. But if you have 18, when you divide by 2, you're going to get a remainder of 0. So the remainder is always smaller than the divisor, right? If it's bigger than divisor, you can continue to divide it. Make sense? Okay. So think about those numbers. If I tell you I have an integer divided by 2 has a remainder 0, what kind of integer is that?
Even.
It has to be even, right? Okay. It's exactly multiple of 2. But if the remainder is 1, you know it's an odd integer. is 2 times integer plus 1. Okay, so we can use the remainders to divide the integers into different categories. If, go back to look at this case, what kind of numbers are even? When you divide that integer by 2, the remainder is, all the even integers, when you divide them by 2, the remainders is what? Huh?
0.
0, right? What about the odd integers? Any odd integer, if you divide it by 2, the remainder is always what? 1, right? Correct? Okay, so by these, if the remainder is 0, which means it's a multiple of 2 times the integer. If it's 1, 2 times the integer plus the remainder 1, right? Okay, so take this approach. How can we divide integers into 3 categories? Divide by one number, you will get 3 remainders. Any integer divided by one number, you will get 3 remainders. Remainder 0, remainder 1, and remainder 2. Divide by one number. 3, right? Okay. Because remember what we said? Your remainder is always going to be smaller than the divisor. So if you take all the integers divide by 3, previously we divide by 2. Although you may think, oh, I didn't divide by 2. I just know all the integers can be divided into either odd or even. But if you take a different view at this, it's the same as dividing every integer by 2. You get 2 remainders. If the remainder is 0, you get all the even. If the remainder is 1, you get all the odd. So similarly, if you look at the integer this way, divide integers by 3. You either get a remainder 0. For example, 18, divide by 3. The remainder will be 0, right? What do we call this kind of number? It's divisible by 3, right? Or, in other words, we call them a multiple of 3. How do you describe a number that is a multiple of 3? Huh? I think algebraically, like a symbolic thing. 3 times k, right? That's multiple of 2, which means 2 times the integer. Multiple of 3 means 3 times the integer. K, where is the integer? So similarly, how would you describe an integer with the remainder 1 after divided by 3? Yes, very good. 3k plus 1. Because I give you an example. Let's say 19. If you divide 19 by 3, what do you get? 19 divided by 3. The remainder is 1, right? And 19 can be written as 3 times 6 plus 1. Correct? Okay. 3 times 6 plus 1. So it's 3 times the integer. Okay, this number we don't care. We only need to know it's an integer. I don't care if it's 6 or 7 or 100. All I need to know is 3 times k plus 1. So numbers like 19 or 22 or 4, they can all be written as this form, 3k plus 1. So these integers are multiple of 3 plus 1. But what about a 5? Is 5 a multiple of 3? Is 5 multiple of 3 plus 1? No, because when you divide 5 by 3, what's the remainder? It's 2, right? So it tells us, like numbers like 5 or 8 or 11, these numbers are 3 times an integer plus what? A remainder 2, right? So the format is going to be 3k plus 2. Correct? Okay. Do we have any other integer? Have we included every integer in here? When you divide any integer by 3, you either get a remainder 0 or 1 or 2. Where you get a remainder 3? No. If you get a 3, you can divide that 3 by 3 again to get a remainder 0, right? You will not get any other remainder. So there will always be 3 cases. If you get take an integer divide by 3. If you get remainder 0, that means that integer is 3k, a multiple of 3. Or if you get remainder 1, that integer is 3k plus 1. because 3 goes into this integer this many times, k times plus a remainder 1. Or if you get a remainder 2, that tells you that integer, 3 goes into that integer k times plus a remainder 2, right? Okay, so that's everything. We are not missing any integer. And any integer you have, for any integer we have, this n, it's either 3k, or 3k plus 1, or 3k plus 2. All right, so does anybody have a question about this? So if not, we can use this to do the second example. Okay. So example 2, prove that for any integer n so n cubed minus n is divisible by 3 is divisible by 3. Now, recall the definition of divisibility. How would you show a number is divisible by 3? Say, for example, I'll say 18 is divisible by 3 because 18, how do you prove 18 is divisible by 3? Yes, because 18 is equal to 3 times the integer. In this case, is 6. And if you look at your notes last Wednesday, we also proved expression 3a plus 3b is divisible by 3 because 3a plus 3b is equal to 3 times a plus b if a, b, and are integers. So that's one of the examples we did last Wednesday. So as you can see, if you want to show something is divisible by 3, in other words, a multiple of 3, you have to be able to write that, factor a 3 out of that expression. So, for example, 18, I can factor 3 out. 3a plus 3b, I can factor 3 out. Now look at this expression. Can we factor out 3 from here? No, we can't, right? Okay, so the approach I tried to use like before, it didn't work. So I'm going to try to do by cases. All right, so previously we did 2 cases, even and odd. Will that work? We can try it. So probably when you get a problem, you don't know whether you should try to divide all the integers into even and odd, 2k and 2k plus 1. Or I should do it by 3 cases, 3k, 3k plus 1, 3k plus 2. So this is my thinking. I'm going to try to do 2 cases, see if it works. So you don't have to copy this down. I'm trying to explain to you how would you know that you shouldn't do 2 cases instead you have to do 3 cases. Suppose I do 2 cases like before. N is 2k, and n is 2k plus 1. So let's try 2k. Plug 2k in there. Replace n with 2k. By the way, what is 2k cubed? 8k cubed. Be careful, don't get 2k cubed. In the past, I saw some students who got 2k cubed. So when you do that, you got to do 3 copies of 2k. 2k times 2k times 2k, that will give you 8k cubed. Or you can use the exponential rule. It's 2 cubed, 8k cubed, it's k cubed. Can we, so after we plugged in, can we factor out of 3? Still not. You can factor out of 2, but not of 3, right? So that tells us, all right, if I do 2 cases, even and odd, I cannot factor out of 3 for this problem. It doesn't work. Previously, it worked because we just need to show it's even. I just need to factor out of 2, but now we want to factor out of 3, which does not work. So that tells me maybe I should do 3 cases. All right, so case 1. So instead, we're going to divide all integers into three categories. First, I'm going to show, okay, this is divisible by 3 if n is a multiple of 3. So let's do n equals 3k. K is an integer. And then after that, I'm going to have to do 3k plus 1, 3k plus 2. So start with this case here. Replace n with 3k. Replace n with 3k. Simplify this. 3k cubed is 27. K cubed minus 3k. Now look at this expression. Can we factor out of 3? Yes. All right, so we factor out of 3. This is not really like the factoring you do in algebra, right? In algebra class, they always ask you to factor out the greatest common factor, which should be 3k, right? But for us, you don't. We don't really, we're not doing factoring for that. We are just need to show this is a multiple of 3. So you can leave the k in there. You don't have to factor out a k. So that would be 3 times whatever that is. It's an integer. You can say this is divisible by 3. I'm going to use the symbols to save some writing. Therefore, 3 divides n cubed minus n. So I think at this point, everyone understands why this is true. So probably you can save some writing instead of saying, oh, the reason why this is multiple of 3 because this is an integer. So k is an integer, that makes this integer. If this is integer times 3, it means 3 goes in there. Okay, so that's the first case. What do we do next?
3k plus 1.
Yes, that's right. So you won't be able to stop here because the problem asks us to prove it's for any kind of integer. See the symbol, any integer, not what we just proved so far. We showed this is divisible by 3 for only for this kind of integer, multiples of 3. So we got to show, okay, next. If n is not a multiple of 3, that's possibly could be a multiple of 3 plus 1. But I can still show it's divisible by 3. So I'm going to do the second case. Replace n with 3k plus 1. When you plug it in for n, make sure you have parentheses for 3k plus 1. Otherwise, you're going to have a mistake right there. Replace n. This is entire expression. 3k plus 1 is our n. 3k plus 1 cubed. Okay, that takes a little bit of time to work out. Okay, so I'm going to go ahead and you can do this after class. How do we do 3k plus 1 cubed? You got to do 3k plus 1 times 3k plus 1 times 3k plus 1. And I guess for those of you, if you forgot how to do this from algebra class, you got to do 3 copies, unless you have memorized the formula. In this class, almost at the end of the semester, I will give you a formula to do this. So you don't have to do like, this many times, okay? But right now, that's all you have to do. And then you have to, so first you multiply out 3k plus 1, 3k plus 1. And when you get an answer, combine like terms and multiply again. So you should have 27k cubed plus 9k squared plus, let's just slow down. So 9k squared plus 18k squared plus 6k plus 3k plus 1. So distribute. Combine like terms, you should have 27k cubed plus 27k squared plus 9k and plus 1. Okay, so go ahead. I'm going to copy that into my, put the question right down here. We get 27k cubed plus 27k squared plus 9k and plus 1. Now subtract 3k minus 1. Don't forget that the reason we got minus 1 is because that plus 1 is in the parentheses, so minus times plus, you get minus. Now we can combine like terms. Can we factor out of 3?
Yes.
Yes. So we got 9k cubed plus 9k squared plus 2. And again, you can say, therefore, 3 divides that. 3 divides this number, n cubed minus n. It means n cubed minus n is divisible by 3. So I just use the symbol to save some writing. So instead of saying n cubed minus n is divisible by 3. Okay, are we done yet?
No.
No. Yes, we have one more case to do. Okay. Like I said, I'm just going to give you at most 3 cases. You never need to do 4 cases or 5 cases. But you need to realize, yes, it's possible that you have to do more than 2 cases. Like I said, if you a lot of papers I published on discrete mathematics, I have to do like more than 2 cases, 3 cases. If you have a very complicated theorem. So let's look at the next one, case 3. Because so far, why cannot we stop here? Because so far, we proved n cubed minus n is divisible by 3 if n is a multiple of 3 or a multiple of 3 plus 1. But what if n is not a multiple of 3? It's not a multiple of 3 plus 1, like a number 5. Number 5 is not a multiple of 3. It's not a multiple of 3 plus 1. You haven't proved that. The problem told us to prove for every integer. You cannot miss anything. But if you only do 2 cases, you are missing like 5, 8, and 11, those numbers. So we're going to do case 3. I think you should be able to finish, do this yourself. So I'm going to go a little quicker. The idea is the same, so we're going to plug that into the expression 3k plus 2 cubed minus 3k plus 2. So for that part, you do have to work out, so in that expression, you just change it to 2 and 2 and 2. Get a 4 here and 12 here. And then you will have to work out. So to save some time, I'm going to go ahead and give you the answer, but you can work that out after your class. For that part, if you work it out, you should get 27k cubed plus 54k squared and plus that would plus 4 and subtract the 3k minus 2. Combining like terms, we get 6. And again, you will be able to factor out of 3. So therefore, 3 divides n cubed minus n. Okay, so we did, now you can stop because we did all 3 cases. So combining all these 3 cases, we proved for any integer, if for any integer, this is always divisible by 3. It doesn't matter if n is a multiple of 3 or a multiple of 3 plus 1 or a multiple of 3 plus 2. And that includes all the integers we have. Okay. Any question? So now I have a question for you. So how do I know whether I should do 2 cases, 2k, 2k plus 1, or 3 cases, 3k, 3k plus 1, 3k plus 2? How would I know? You can always try. I would always try the 2 cases, see if it works. I did try, I found out it didn't work. See, I tried the 2 cases, it didn't work. I cannot factor out the 3, right? And then I tried 3 cases. But any quick hint that can tell us we should do 3 cases for this case? Yes, divisible by 3 probably should do 3 cases because it has 3 in there. 3k, you can factor out the 3. 3k plus 1, you can still factor out the 3. 3k plus 2, there's a 3 there. So that's a quick hint for you. If you have, they want you to prove it by divisible by 3, most likely you have to do 3 cases. Not always. Sometimes 2 cases may work. Sometimes maybe you don't have to do any cases, just the 1 case. You may be able to factor out the 3. So you always check, can I factor out the 3? If you can't, try to do 3 cases. Okay, so similarly, if I want you to prove something is divisible by 4, so maybe you have to do 4 cases. Which 4 cases? 4k, 4k plus 1, 4k plus 2, and what? 4k plus 3. Because any integer, if you divide it by 3, divide by 4, you're going to get 3 remainders. With the remainder 0, or remainder 1, or remainder 2, or remainder 3. If the remainder is 0, you're going to get 4k. If the remainder is 1, you get 4k plus 1, or 4k plus 2, and 4k plus 3. But you may not have to do 4 cases. Maybe 2 cases will also work. So the homework question, it's an option, but let's look at the homework question number 40. The number 40, that they do want you to prove it's divisible by 4, but I would not try. If you want to do 4 cases, yes, certainly it will work. But 4 cases, that's a lot, right? So I would try, for this question here, I would try 2 cases first. When by looking at it, can you factor out the 4? The first thing you always check is, can I just factor out the 4 directly? If you can't, try 2 cases, well, whatever. So, although it is asking us to prove divisible by 4, 2 cases it will work because if you put a 2k here, you will get a 2. And 2k here, 2k plus 2, you can factor out another 2, right? And 2 and 2 will give you a 4 already. So, for the homework question number 40, 2 cases should work. So I think all the homework questions that I gave you, you only need to do 2 cases, I think. Yeah. But later, on the second exam, you will have 3 cases. So now I'm going to do a question kind of similar to number 37. Prove the square of any integer has the form 4k or 4k plus 1. So I am going to do example from the textbook, example 3, which is on page 162, theorem 3.4.3. Asks us to prove the square of any odd integer. Oh, I forgot to switch. Any odd integer has the form 8m plus 1 for some integer m. Okay. All right. So what do we start with? What's given? What kind of number is given? Any what? Odd integer. Okay. So it's different from the previous 2 examples. Previously, it just says for any integer. It didn't tell us what kind of integer it is. So it could be even, it could be odd, it could be multiple of 3 or not multiple of 3. Over here, they did tell us it's an odd integer. So when you start, you can assume this integer is odd. We don't have to worry about it even. So let 2k plus 1 be an odd integer. Where k is the integer. All right, now we want to show the square of this odd integer is a multiple, 8m plus 1. What does that mean? It means it's a multiple of 8 plus 1. So that's what we need to show. We take 2k plus 1 squared. I think the way I'm doing it is slightly different from textbook. I want to show you a different way maybe after this if I have time today. So first we're going to do this way. So 2k plus 1 squared. So I'm going to do it. So I think we had examples like this. I'm going to just go ahead and write down the answer. You do FOIL, 4k squared plus 4k plus 1. All right. Does it have this format 8m plus 1? No, it does not, right? So if you want to get this format, you have to be able to, the plus 1 does match. There's a plus 1, I do have a plus 1. But for the rest of the expression, I need to be able to factor out 8. Can I factor out 8? No. Okay. So I'm going to start from here and do 2 cases instead of, there is a different way to do this. I will show you in a second. So when I get here, I stuck. I cannot factor out 8. So I'm going to do 2 cases from here. This k, what is this k? This k is an integer, right? If it's an integer, I can do 2 cases or 3 cases. This integer, I could do odd integer or even integer. So here's what I'm going to do. Case 1, if k is even integer, 2, I'm going to try not to use the letter they already used, the m. So I'm going to use n. So you can do the same thing when you do the homework question. They ask, oops. Uh-oh, did I mess it up? I hit play back. How do I get rid of that? What is that? I hit it again. Okay. Well, okay. Maybe I just hit. Okay, let me try the camera. Oh, there what? Okay, sorry. Thank you. Okay, so I try to press. Okay. So the homework question, they want you to show is 4k or 4k plus 1. So I would try not to use the letter k. Use the different letters like m or n, whatever. Try not to use k. You can use k, but I think you may get confused at the end. Maybe if you have a very good background in algebra, you may understand this better. But at this point, trying to avoid the letter they already have. So, for example, they use the m in here. I'm going to try not to use m. I try to use a different one. Okay, so k. Now this k right here is an integer. So I'm going to do 2 cases. If k is an even integer, or k is an odd integer. So start with case 1. I'm going to continue from here. So 2k plus 1 squared equals 4k squared plus 4k plus 1. Now let's plug 2m into the expression for that k there. I get 4 times 4 is 16n plus 8n plus 1. Now take a look. Can I factor out 8 from here? Yes. So we got 2n squared plus m plus 1. And this will be the letter m they want. So this will be my m, which is 8n plus 1. So that m is 2n squared plus n. So that's why the reason I try to use a different letter. So I won't end up with m equals 2m squared plus m, right? Okay. So I guess I can specify where m is equal to 2n squared plus n. So look, I proved the square of an odd integer is equal to 8 times the integer plus n, plus 1. That m here is an integer. But I so far only did it for one case, if that k is even. So similarly, if that k is odd, if it's not even, I can prove this. same way. So we want to do the second case, case 2. So case 2, what if k is not even, which means it has to be odd? And I plug into that expression the same way. 4k squared plus 4k plus 1, which equals 4 times 2m plus 1 squared plus 4 times 2m plus 1 plus 1. Okay, so here we have, all this is algebra, so you can work out yourself later if you just want to copy down my solution now. Now we combine like terms. Less than that, 24n plus, okay, so over here you can combine 4 and 4 and 1 to get 9, right? But I don't want to do that. I just want to combine this 4 and that 4 to get 8. I want to leave that 1 by itself. Do you know why? Because the problem told us to prove the answer is going to be 8 times the integer plus 1. So that's why I want to leave that 1 there. I don't want to combine to 9. For the rest of the expression, I try to factor out 8, which I can. Okay, now I get 8 times m plus 1, where m is equal to 2n squared plus 3n plus 1. So we're done. Okay, so take a look at this question one more time. So they want us to prove after we square an odd integer, we should be able to get a multiple of 8 plus 1. When I did that, I found out I cannot get a multiple of 8. I can only get a multiple of 4. So that's why I did continue to do 2 more cases. Because this k right here could be even or odd. So that's why I did it even. If this k is even to n, I can factor out 8. If it's not even, then it has to be odd. I can still factor out a 8 in the end. Okay, so we proved it doesn't matter what that k is. Could be even or odd. This k, I can always prove I can factor out 8. Yes, yeah, because there's already I'm already able to factor out a 4, right? So if I can factor out a 2 from there, so 2k plus 1, it would work. The textbook did a different approach. So this is maybe I call it proof 1. There's a different way. Proof 2. So I'm going to try to show you the way the textbook did. All right. So the other way to do the problem is I can start from very beginning to talk about this odd integer. Go back to what we had before. So all the integers can be divided into 4 categories. 4k, 4k plus 1, 4k plus 2, 4k plus 3. Now out of these 4 categories, which is 4k even or odd? It's all even, right? Because it's 2 times 2k. Apparently it's even right here. 4k plus 2, is this even or odd? Even. Why? Because you can factor out a 2, which 2 times the integer makes it even again. And these 2 will be odd, right? Because 4k is even plus 1, you get odd. And 4k plus 3, the same thing, it's odd because you can write it as 4k plus 2 plus 1. And we already know 4k plus 2 is even. So even plus 1 is odd. Okay. And go back to the question again. It says the square of any odd integer. So any odd integer, instead of using this format, 2k plus 1, I'm going to use this format, 4k plus 1 and 4k plus 3. Make sense? Okay. So any odd integer. So you can see there's not just one way to describe an odd integer. Of course, you can use 2k plus 1. Yes, that is odd. But you can also describe it as either 4k plus 1 or 4k plus 3. And think about it, it makes sense. Any odd integer is either a multiple of 4 plus 1 or a multiple of 4 plus 3. Right? Okay. So if you have 1, 1 is a multiple of 4 plus 1. If you have 3, it's a multiple of 4 plus 3. If you have next odd integer will be 5. 5 is a multiple of 4 plus 1, right? Next integer 7 is a multiple of 3 plus 7. So all integers can also be written in a different form, 4k plus 1, 4k plus 3. So that's what the textbook did. And this way, I go ahead and start case 1. I guess, case 1, maybe you can add a little bit explanation. So I kind of have 3 minutes left, so I'm going to try to hurry a little bit here. So let 4k plus 1 be an integer. Okay, that's not the best way to write it, sorry. I would say any odd integer can be written as 4k plus 1 or 4k plus 3, the case integer. So now you can do case 1. Consider 4k plus 1. 4k plus 1 squared. So we get 16k squared plus 8k plus 1. Can we factor out 8 from here? Yes, right? Okay. So it's 8m plus 1. Now do case 2, which is 4k plus 3. So do the same thing. Case 2. You have 4k plus 3 squared. 16k squared plus 24k plus 9. So I'm going to rewrite that 9 as 8 plus 1. That's 9 right here. Write 8 plus 1. So I can factor out 8 from the previous expression plus 1. So that would be 8m plus 1 again. Okay. Right, so this way might be a little easier, right? I guess, but you do have to know any odd integer can be written as either 4k plus 1 or 4k plus 3. Why is that? Because of this. Because all the integers can be divided into 4 categories. 2 of them are even. Only the other 2 are odd. So that's why I only need to check this and that. All right, so that will be all for today. And this homework is due, I will make it due next Wednesday instead of Monday, so you can focus on the test. Okay, so on Wednesday we're going to have a review class. All right, that's all for today.
Your meeting has ended.